thank you. You might be wondering what the hell is this talk about, but the thing is that the next week there will be some talks about normal diffusion, scattering maps, shadowing of the normally invariant hyperbolic manifolds, and the key assumption usually in that kind of problems is the fact that the unstable and stable manifolds of some invariant objects intersect transversally. And so the work we're having in progress addresses the problem of robust non-transversality, which we find in some models in applications. And so hopefully you will find it interesting as well. So to start with, I will just consider some, oh, what the hell, it doesn't work. So to start with, let's consider some simple toy model. It comes actually from game theory, so I don't want to offend you and talk too much about this. So there are some matrices, and we consider some OD in R4 on some compact subset. So it's an OD with some constraints, okay? And it's like OD with some, depending on the parameter family. And so the thing is that what's interesting in this model is that we've got normally hyperbolic invariant manifold, which is disconnected, so it consists of two-dimensional center manifolds. There are 6 of them, and for each of these center manifolds, the unstable manifold of this piece coincides with the stable manifold of this piece, and so on, so on. So we've got such a loop of 6 homoclinic channels, and so we want to understand the dynamics in the neighborhood of this homoclinic channel, which is like a non-transversal homoclinic channel. And so the naive approach would be just to investigate each of the scattering maps between the 6 pieces and try to establish some kind of shadowing property. So the thing is that we take some point close from the unstable manifold here, and we integrate it non-rigorously, and if it just approaches this piece, we just project it on this manifold, and we see what's happening. So, in the other words, we're taking points from unstable manifold of some fixed periodic orbit, integrate it, and then project it. And so, here on the horizontal line, we've got parameterization by time of this periodic orbit, and on the vertical line, we've got parameterization of the periodic orbits on the next piece by some energy function. So it means, what does this graph shows is exactly which stable manifolds of which periodic orbits from the next piece are intersected by the unstable manifold of this periodic orbit. So if we project this graph onto the vertical line and redo this computation for like many periodic orbits, then we will obtain such a graph. And it should tell you something about the scattering map. So from the works of Tulayev, Kiriki, Shinohara, and many famous guys, we can conclude that if such a set-valued function which imitates scattering map, its minimum and maximum value are non-decreasing, then we can expect some complicated behavior. But as I said, first we need to establish some shadowing. Okay, so if this intersection of this stable and unstable and stable manifolds was transverse, and this homoclinic channel was in fact a transverse homoclinic channel, then using this method of covariant relations like in these 2 papers, we would be able to establish infinite shadowing, and we would be able to say something about statistical properties and behavior in the vicinity of this homoclinic channel, and it will be fine. But the thing is that we cannot use this method. Okay, and the fact is that it's easy to verify that if you take a point which is close to the unstable manifold of this piece, but not on the stable manifold, then after some period of time it just goes to the center of the phase space. So it seems that dynamics are kind of trivial, at least asymptotic dynamics. So that's not a good example to investigate. So what we want to not only investigate some kind of simple toy models, but also explain what fails in this example. So we consider a simple one. So instead of squares, we are interested in some disks, okay, filled with periodic orbits, and this disk is immersed in R4, and the stable and stable manifolds of this disk coincide, so we've got non-transverse homoclinic channel. Yes. Okay. And so this system can be looked schematically as a Cartesian product of rotation along the circle and homoclinic loop. Okay, and so we derived the normal form close to this point for any R5 from the disk. So the normal form locally looks like this. Never mind, it's just formula. But the key assumption is a probability on C that these coefficients E plus C, whatever that letter is, sum up to something smaller than 0. So it means that in the limit, if you start with a point somewhere close to this homoclinic loop, the trajectory will accumulate on this homoclinic channel. Okay, so the dynamics seem to be trivial because we accumulate on the homoclinic channel, but we can say something about the limit properties of the limit set. Okay? So this is something that we can verify in our previous model that's not satisfied. Okay? Good. So if we put a test section here, then we investigate instead return map. So the return map looks quite disgusting. And if we introduce some logarithmic-like coordinates, then the return map still looks disgusting and has this garbage at the very end, which is not differentiable at 0. Okay? So we are interested what are the dynamics of this return map. Okay, that's the question. And so we keep in mind that this contraction on the V coordinate is strong. So the contraction to the homoclinic channel is strong. Okay, that's the key point. So we consider truncated map without this garbage, and we ask ourselves what is the relation between the dynamics of the true return map and the truncated map. Okay, so without the garbage. And so we consider some kind of like artificial map. So we take the first coordinate of the true return map and the last 3 coordinates of the true return map, but written in the logarithmic coordinates. Okay, so since we've got a strong contraction to 0 of the first coordinate, and we find out that there is invariant foliation of the phase space of this form, we find out that there is a one-to-one correspondence between the limit properties of the return map and the truncated map. So in the limit, the dynamics of the return map is the same as the dynamics of the truncated map. Okay? So we've got a map to investigate, a truncated one. So we ask ourselves, what are the dynamics? What can be the dynamics of such a map? So it can be trivial, or it can be very complicated. There might exist blender, for example. There might exist pseudo-hyperbolic attractor, like Lorentz-like attractor, and this is an example of coefficients you have to choose, and you can find Lorentz-like attractor, which is just a simple application of these methods for these 2 papers. Okay, so it seems that even in the most simple toy model, the dynamics can be very complicated. Obviously, I fit in some assumptions, which makes this stuff very easy to investigate. And so we've got some other models as well to investigate where the non-transversality is robust. And that's a question for the future generation of mathematicians, what to do with this fact. Okay, so thank you for your attention. I hope you have some questions. Grazie.